Alright, let's go. Number 10. The Pigeon Problem. In 1963, Arno Penzias and Robert Wilson were not doing cosmology. They were two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, handed a 20-foot horn-shaped antenna that had been built to bounce signals off the Echo balloon satellites. The satellite work was finished. The instrument was theirs. Before they could use it to survey the radio sky, they had to characterize every source of noise inside it and subtract them all away. The expected result was silence. Every known contributor to the noise budget was accounted for. The atmosphere, the receiver electronics, the ground radiation leaking over the horn's rim, the residual heat of the antenna structure itself. Subtract all of it and the sky at 4,080 megacycles should have read essentially zero. That was the whole point of the calibration. It read 3.5 degrees above zero. Everywhere, in every direction they pointed, at every hour of the day, through every season. Penzias and Wilson reported an excess antenna temperature of 5 Kelvin plus or minus 1 Kelvin in a paper of barely 600 words published in the Astrophysical Journal in 1965, volume 142, page 419. On the facing pages sat a companion paper by Robert Dick, Jim Peebles, Peter Roll, and David Wilkinson at Princeton, 30 miles away, explaining what the two men had found. Before they got there, they killed every alternative. Interference from New York City, ruled out. The signal was isotropic, and the city was not. A residual from the 1962 high-altitude nuclear tests, ruled out. It should have decayed, and it did not. A fault in the receiver, they rebuilt it. Loose rivets in the horn's throat, they taped over every seam with aluminum tape. And a pair of pigeons had nested in the antenna and coated its interior with what Penzias described in his notes as a white dielectric material. They caught the birds. They shipped them away. The birds flew back. They scrubbed the antenna clean by hand. The hiss did not move. Everything that has ever happened to you happened inside that hiss. It is still arriving, at your skin, right now, several 100 million photons per second per square centimeter. The greatest discovery in the history of observational cosmology spent 2 years classified as equipment filth. What else are we currently calling noise? Once you accept the hiss is real, the next question is what is written inside it. Number 9. The sound of the first plasma. Jim Peebles and Jerry Yu at Princeton were working on a bookkeeping problem in 1970. Before recombination, the universe was an ionized soup of protons, electrons, and photons, all tightly coupled. They wanted to know formally how density perturbations in that soup would evolve, a routine exercise in fluid dynamics applied to a fluid nobody could see. Standard physics gives an unambiguous answer for a compressible fluid under gravity. Gravity pulls matter into a dense region. Radiation pressure pushes back out. The result is not collapse, and it is not dispersal. It is oscillation. The plasma should ring, with a sound speed of the speed of light divided by the square root of 3, which means the early universe was not a picture. It was a recording. Peebles and Yu published the prediction in the Astrophysical Journal in 1970, volume 162, page 815. Rashid Sunyaev and Yakov Zeldovich reached it independently in Moscow the same year. Confirmation took 3 decades. In April 2000, Paolo de Bernardis and the Boomerang collaboration published in Nature, volume 404, page 955, the first clear detection of the acoustic peak. A spike in the angular power spectrum at multipole 220. Planck has now measured the harmonic series out past the 7th peak. Every attempt to produce that peak structure without primordial sound failed. Topological defects, cosmic strings, and textures were the leading rival through the 1990s. Strings produce a single broad bump and no harmonic series, the data killed them outright. Pure isocurvature initial conditions predict the first peak in the wrong place, shifted by a factor of roughly 2 in multipole. Foreground contamination cannot manufacture a harmonic ladder. And a universe with no dark matter cannot suppress the second peak relative to the first, but ours does, and from the exact size of that suppression the baryon density falls out, 4.9% of the total. Every atom in your body was weighed by that measurement before any atom in your body existed. The frequencies were around 50 octaves below anything a human ear can register. What else is the universe currently saying at a pitch we cannot hear? The recording is nearly perfect. Nearly number 8, the cold spot. Patrizio Vielva and his colleagues at the Universidad de Cantabria were not hunting for anomalies. They were testing a statistical method, spherical wavelets, against the first year of Dove map data, checking whether the temperature fluctuations were Gaussian, as inflation predicts. It was a validation exercise on a new tool. Inflation makes a specific promise. The fluctuations should be a Gaussian random field. No preferred locations, no features, nothing that stands out from the statistics of pure noise. Rare cold regions exist, but their sizes and depths should follow a known distribution with no outliers. One patch in the constellation Eridanus refused to fit. Vielva and colleagues reported it in the Astrophysical Journal in 2004, volume 609. Page 22. Marcos Cruz and collaborators confirmed and characterized it in monthly notices of the Royal Astronomical Society in 2005. A region roughly 5 to 10 degrees across, about 70 microkelvin colder than the mean, with a probability of arising by chance in a Gaussian sky quoted at around 1%, and around 0.1% by some wavelet measures. The explanations came in and died in sequence. A statistical fluke possible, but the significance survived Planck's independent higher resolution maps. Galactic foreground contamination, the spot is well off the galactic plane and shows no frequency dependence. A supervoid along the line of sight, cooling photons by the integrated Sachs-Wolf effect. Istvin Saputi's team reported exactly such a void in Emin-Ras in 2015, some 1.8 billion light-years across. Then Ruari Mackenzie and Tom Shanks at Durham surveyed the galaxies inside it in 2017 and found no void deep enough. Even the original claimed void could only account for around 10% of the temperature deficit. And the remaining candidate, a collision scar, a bruise left where our inflating bubble struck another one. The hypothesis Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris tested in physical review letters in 2011 and found no significant support for. This is the only observational evidence anyone has ever claimed for a universe other than this one. It rests on a cold patch the size of your thumbnail at arm's length. If it is a bruise, something hit us. Where is whatever hit us now? The cold spot at least sits in one place. The next anomaly points somewhere. Number 7. The Axis of Evil. Anglica de Oliveira Costa, Max Tegmark, Matthias Zaldariaga, and Andrew Hamilton were doing quality control in 2003. They wanted to know whether DewMap's largest scale measurements, the quadrupole and octupole, the two broadest patterns on the sky, were clean enough to trust, or whether galactic emission was leaking into them. A routine systematics check. The cosmological principle requires that these patterns have no preferred orientation. The quadrupole is a structure spanning the entire observable universe, imprinted 13.8 billion years ago. Its axis should point in a random direction, uncorrelated with anything local, and certainly uncorrelated with the geometry of one small planetary system. The quadrupole and the octupole were aligned with each other, and their common axis lay close to the ecliptic, the plane of Earth's orbit. De Oliveira Costa and colleagues published the analysis in Physical Review D in 2004, volume 69, article 063516. Caitland and Ju Maguejo at Imperial College London named it in Physical Review Letters in 2005, volume 95, article 071301, The Axis of Evil. The alignment between the two multipoles alone occurs by chance in roughly one sky in 100. The additional correlation with the ecliptic and the equinoxes pushes it, by some estimates, to around 1 in 1,000. Planck, a completely independent instrument with different optics, different scanning, and different systematics, reproduced it. The candidate explanations have all struggled. Residual galactic foreground, the alignment is with the ecliptic, not the galactic plane. And subtraction methods that differ wildly still leave it. a map-specific instrumental artifact eliminated by Planck. Local dust in the solar system zodiacal emission too weak by orders of magnitude at these frequencies. Statistical fluke arising from looking at many quantities and reporting the strange one, the a posteriori problem, remains the most defensible answer, and it is not so much an explanation as a refusal to be impressed. The largest structure in the observable universe appears to know which way our planet goes around our star. If that is coincidence, we drew it. If it is not, what is the plane of your orbit doing in a photograph taken before the Earth existed? There is a second problem with those same large scales, and it is a problem of absence. Number 6. The missing large angle power. Gary Hinshaw and the COBE team were producing the final differential microwave radiometer maps in the mid-1990s, the definitive version of the data that had already won the mission its Nobel. The task was to characterize the correlation function, take any 2 points on the sky, note their angular separation, and measure how similar their temperatures are. The standard model predicts a specific curve. At large angular separations, above roughly 60 degrees, there should be a modest but non-zero correlation, set by the near-scale invariant spectrum inflation produces. It is one of the oldest and least exotic predictions in the framework. Above 60 degrees, the correlation is very nearly zero. The sky is flatter than it should be. Craig Copey, Dragan Huderer, Dominic Schwartz, and Glenn Starkman formalized the deficit with a statistic called S1/2, applied across COBE, WMAP, and Planck data in a series of papers from 2007 onwards. In the cleanest cuts of the sky, fewer than 1 in 1,000 simulated CDM skies show as little large-angle correlation as ours. The quadrupole amplitude itself came in far below the concordance prediction, a discrepancy visible in the very first COBE release in 1992 and still present in the Planck 2018 legacy maps. The explanations have not held. Cosmic variance, with only one sky and only 5 independent quadrupole components, chance is a real possibility. But the effect has now persisted across 3 missions spanning 26 years, and no additional data can ever resolve it, because there is no more sky. Galactic cut artifacts, the deficit strengthens when the galaxy is masked more aggressively, which is backwards for a contamination story. A finite or non-trivially connected universe. Too small to support the longest wavelengths, searched for exhaustively by match circle tests in new map and Planck data, and never found. The universe owed us structure on the largest scales, and did not deliver it. Everything we know about the beginning rests on a spectrum whose longest note is missing. What was cut off, and by what? 2 large-scale anomalies invite a third. Number 5. The Hemispherical Asymmetry. Hans Christian Erichsen and his colleagues in Oslo were performing a Gaussianity and isotropy audit of WMAP's first-year maps in 2003. The method was almost naive. Divide the sky into hemispheres along many different axes, measure the fluctuation power in each half, and confirm the 2 halves match. It was expected to be a null test. The cosmological principle is the foundation the entire framework stands on. On large scales, the universe is homogeneous and isotropic. No hemisphere is special. Split the sky any way you like and the statistics should agree. They did not agree. One half of the sky fluctuates measurably more than the other. Erichsen and colleagues published in the Astrophysical Journal in 2004, volume 605, page 14. The effect is well described as a dipole modulation of the fluctuation amplitude, with an amplitude of roughly 7% on large angular scales, at a significance of about 3 sigma. Planck's isotropy and statistics analyses in 2013, 2015, and 2018 recovered it with an independent instrument. The preferred direction sits in the southern galactic sky, not far from the cold spot, and not unrelated to the axis of items 7 and 6. The failure parade here is short and unsatisfying. Instrumental beam asymmetry or scanning strategy, Map and Planck scan the sky in entirely different ways, and both see it. Foreground residuals, the asymmetry is scale-dependent in a way that no known galactic emission reproduces, fading above multipulse 600. The look elsewhere effect, This is the strongest objection, since the direction was chosen after seeing the data, and 3 sigma with a freely chosen axis is not 3 sigma. Theoretical fixes, a superhorizon perturbation, a gradient in the inflaton field across our entire observable volume, can be constructed, but each one predicts other signatures that have not been seen. 3 separate large-scale anomalies, all in the same rough region of sky, all in the data that describes the universe you woke up inside. Either we are looking at the residue of 3 unrelated flukes, or at one thing we have not named. Which would you rather it be? Anomalies are one kind of failure. Announcing a discovery that is not there is another. Number 4. The discovery that wasn't. The BICEP 2 team, led by John Kovac, Clem Pryke, Jamie Bach, and Qiaolin Kuo, spent 3 seasons at the South Pole doing something narrow and technical, measuring the polarization of the microwave sky over a small, unusually clean patch at a single frequency, 150 gigahertz. They were looking for a twist. Inflation predicts that gravitational waves from the first fraction of a second should imprint a curl pattern in the CMB polarization, B modes, that ordinary density fluctuations cannot produce. Detecting them would be direct evidence of quantum gravity written on the sky. It was widely considered a Nobel guaranteeing measurement. They found the curl. On 17 March 2014, they announced it at a press conference at Harvard. The reported value was a tensor to scalar ratio R of 0.20, with an upward uncertainty of 0.07 and a downward uncertainty of 0.05. A rejection of 0 at more than 5 sigma, published in Physical Review Letters in June 2014, Volume 112, Article 241101. Qiaolin Kuo's video of Andre Linde being told at his front door, 30 years after he helped invent inflation, went around the world. The explanations were tested in public and in order. Instrumental systematics, BICEP 2's own null tests were clean, and this was never the weak link. Gravitational lensing converting E modes to B modes. Real. Accounted for. Far too small. And polarized emission from magnetically aligned dust grains in our own galaxy, the one component BICEP 2 could not separate, because it observed at only one frequency. Planck, observing at many, published its dust polarization measurement of that same patch of sky in late 2014. The joint BICEP 2, Kekulé and Planck analysis appeared in Physical Review Letters in 2015, Volume 114, Article 101301. The signal was consistent with dust. The limit today stands at R below 0.036. The most celebrated cosmological result of the decade was our own galaxy's dirt, seen through a single filter. Everything else on this list was measured by people exactly this careful. How do we know which of these entries is the dust? Not every surprise in that light is a mistake. Some of it is evidence. Number 3. The fingerprint map. Elaine Blanchard and Joseph Schneider worked out in 1987 what should happen to CMB photons on their way here. It was a theoretical exercise in general relativity, not an observational proposal. Nobody had instruments remotely sensitive enough. Every galaxy cluster and dark matter halo the light passed would bend it slightly. The standard picture treats the CMB as a snapshot of the last scattering surface. But the photons have traveled for 13.8 billion years through a universe that grew lumpy behind them. Gravitational lensing should smear the acoustic peaks and convert some E-mode polarization into B modes at the level of a few arc-minutes of deflection. The distortion is measurable, which means the light carries a record of everything it passed through. Kendrick Smith, Oliver Zahn, and Olivier Dore reported the first detection in Physical Review D in 2007 by cross-correlating MAP with radio galaxy catalogs. Sudeep Das and the Atacama Cosmology Telescope team published the first detection from CMB data alone in Physical Review Letters in 2011, Volume 107, Article 021301. Planck's lensing measurement reached roughly 40 sigma. The ACT DR6 lensing analysis released in 2023 mapped the projected mass over about 9,400 square degrees of sky and constrained the clumpiness parameter to a few percent. What makes this the sturdiest item here is that its alternatives were all eliminated first. A pure primordial explanation for the peak smearing fails, because the effect correlates with the positions of actual known galaxies and quasars. Instrumental beam smearing fails, because it is not correlated with any external catalog. Foreground emission fails, because the lensing signature is achromatic, it does not change with observing frequency, and every galactic contaminant does. The oldest light in existence arrived carrying a map of the invisible mass it brushed past on the way to your eyes, including the dark matter that has never been detected in any laboratory. We can weigh what we cannot see, using light emitted before matter had organized into anything at all. So why can we not agree how fast it is all moving apart? That disagreement is the sharpest number in cosmology. Number 2. The two speeds of the universe. The Planck collaboration's task through the 2010s was calibration in the deepest sense, fit the 6-parameter standard model to the acoustic peaks, and read off the universe's contents and expansion rate. Adam Rees and the SHOW-ES team, meanwhile, were doing the unglamorous work of the distance ladder, Cepheid variables in nearby galaxies, calibrating the Type 1a supernovae that measure distance further out. Two independent routes to the same quantity. One infers the expansion rate today from physics at 380,000 years old, the other measures it directly in the local universe. They should converge. They have converged on different answers. Planck's 2018 legacy release gives a Hubble constant of 67, 4 kilometers per second per megaparsec plus or minus 0.5. Rees and colleagues, publishing in the Astrophysical Journal Letters in 2022, volume 934, page L7, using over 1,000 Cepheids observed with Hubble, gives 73.04 plus or minus 1.04. The disagreement stands at roughly 5 sigma, and it has grown, not shrunk, as both measurements improved. Every escape route has been tried. Cepheid crowding and blending in distant galaxies, JWEST's sharper infrared imaging was expected to dissolve the discrepancy and instead confirmed the Hubble-based photometry. Errors in the geometric anchors, Gaia parallaxes tighten them without moving the answer. Local underdensity, the idea that we sit in a void expanding faster than average, the required void is larger and emptier than galaxy surveys allow. Early dark energy, extra-relativistic species, evolving dark energy, each can shift the CMB inferred value, and each then breaks the fit to some other dataset. And an unknown systematic in Planck, the ACT and South Pole telescope results reproduce the low value independently. One universe. Two measurements. Both made by people who have spent decades trying to prove themselves wrong. The number that sets the age of everything, including the interval between your birth and now, has two values. What are we doing wrong at the very center of the theory? All of these problems share one final constraint. Number 1. The last scattering surface. The question of when the universe became transparent was worked out as a problem in atomic physics, not cosmology. Yakov Zeldovich, Vladimir Kurt and Rashid Sunyaev in the Soviet Union, and Jim Peebles at Princeton, independently in 1968, calculating how hydrogen recombination proceeds in an expanding plasma. A chemistry problem, essentially, the result is unambiguous. Above about 3000 Kelvin, hydrogen is ionized, free electrons scatter photons constantly, and light cannot travel. Cool below that threshold and electrons bind to protons, the fog clears and photons stream freely, forever. That transition happened once, at a redshift of about 1090, roughly 380,000 years after the beginning. And it left a wall. The surface has a measurable thickness, a redshift interval of about 200, corresponding to some 115,000 years of blurring. Everything before it is opaque to every form of electromagnetic radiation. Not dim, not distant. Opaque, no telescope built at any point in the future, at any wavelength, at any aperture, will ever see through it, because there was nothing to see with. The workarounds are all still theoretical. The cosmic neutrino background decoupled at 1 second and would carry information from far earlier, it has never been directly detected, and the detection problem is not close to solved. Primordial gravitational waves would pass straight through the plasma, which is precisely what Bicep 2 thought it had found, and the limit on them keeps tightening. Spectral distortions in the CMB energy spectrum encode some pre-recombination physics. Proposed missions to measure them have not flown. Everything that happened in the first 380,000 years, inflation, baryogenesis, the origin of the matter you are made of, sits permanently behind that wall. You are looking at the edge of what can be looked at. What do you do with a question that is not hard but closed? The universe is not confused. We are. Every entry on this list sits inside the most tested theory we have, not out at its ragged edges, but at its load-bearing center. The temperatures match to 5 decimal places, and the axis points at our orbit. The model predicts the peaks perfectly and cannot agree with itself about how fast we are moving apart. We have built the most precise description of reality in the history of our species, and it is precise enough that we can now see, clearly and quantitatively, exactly where it fails. That is not ignorance. That is ignorance with error bars. If you want to see more videos like this, click the video on screen now.